Hey everybody, this is the Friedel Acetylation Lab. Here's the outline for this video. I'll be going over the reaction, some of the reaction conditions, and the procedure in general. Then I'll be going over some of the properties of the molecules we'll be using or producing. So I'll talk about the rules of aromaticity and go over the 18 electron rule for transition metals. Then I'll be talking about column chromatography for a little bit, and I'll show the actual experiment in the lab. Here's the reaction that we'll be doing. We'll be taking ferrocene and using aluminum chloride and acetyl chloride, adding a ketone group onto that molecule to make the monoacetylferrocene and the diacetylferrocene products. Unlike the Cannizzaro reaction, this is not a 2-to-1 ratio from the reagent to the products. It's just the progression of the reaction, whether it was able to add another ketone to form the di product from the mono product. So it'll be a 1-to-1 ratio from the reagent to each of the products. Initially, we'll be forming the acylium ion using aluminum chloride and acetyl chloride as the reagents so that the pi electrons from the ferrocene molecule can react with it and form the acetylferrocene products that we desire. The ferrocene compound is pretty cool. We have two cyclopentadienides held together by an iron cation in the middle, and each of the rings is a cyclopentadiene with a negative charge on it. And that negative charge is equally dispersed on each of the carbons through resonance, so we can draw the molecule like this because it actually ends up being aromatic. And just as a reminder, here are the rules of aromaticity. The molecule must be cyclic, it must be fully conjugated, it must be planar, and it must follow Huckel's rule of 4n plus 2 pi electrons. So if we look at the cyclopentadienide, it meets all that criteria and is an aromatic ring. Ferrocene is also a very stable compound because it fulfills the 18 electron rule. Now, usually in organic chemistry, we're mainly focused and consider the octet rule, but with transition metals, they have 5 additional d orbitals. Therefore, they can hold 10 more electrons in their valence shell. So their full octet per se, or their full valence shell, would be 18 electrons instead of 8. So if we look at iron, in our case it has a positive 2 charge on it. So it would basically have the same electron configuration as chromium, meaning that it has 6 valence electrons. And each ring also has 6 valence electrons, which they share with the iron atom, adding up to a total of 18 valence electrons. Both the aluminum chloride and the acetyl chloride reagents are highly reactive with water. One of the reactions you probably recognize from your OChem 2 class, where acetyl chloride can react with water to form acetic acid and hydrochloric acid. So to keep as much water out of the reaction vessel as possible, we'll be using a Claisen head adapter again and adding the reagents through a needle and a syringe. Once the reagents are all added, the solution should turn a deep purple. If it doesn't turn that color, then we would have to start over. And then once the reaction is completed, we'll place the solution directly into ice to quench that reaction. Since the reagents are highly reactive with water and react very exothermically, we'll be placing it directly into ice rather than just water. From here, we'll neutralize everything using NaOH since ketones are pretty stable in basic solutions. Then the products can be extracted with methylene chloride and the extracts dried with sodium sulfate, and then we can evaporate the solvent off, leaving our crude products. Now, you may be wondering why these charged compounds would move into the methylene chloride solution when we do the extractions. Usually when we see charged compounds like this, we assume that they'll go into the polar aqueous phase, because that's a more stable interaction for them. And that has to do with the sandwich interaction between the rings and the iron metal. All the charge is concentrated in the middle, so when we add some solvent like methylene chloride, for example, all it sees and all it interacts with is the aromatic rings on the outside and doesn't interact with the charged center. So all 3 of these compounds are basically just organic and will move into the organic phase when doing the extractions. To separate the 2 products from each other, we're going to be using column chromatography, which separates things based off of their polarity. So if we had any ferrocene left over from the reaction, it would be the least polar. Basically, it's just the 2 rings on the outside. And then the mono product increases in polarity by a little bit with that additional acetyl group. And then the di product would be the most polar since it has 2 acetyl groups. We'll be using alumina for the column, which is a polar compound, so the more polar products will be retained in the column longer. And this is how we'll set it up. We'll block the bottom using some glass wool. then place some Ottawa sand on top, and then add about 8 to 10 inches of the alumina, on top of which we'll add the product, and then add just a little bit more Ottawa sand so that when we add the solvents, it'll hold the product in place. And from there, we can start eluting the column and separating our two products. So the less polar compounds will elute out of the column first, but by increasing the polarity of the solvents, we can start eluting the more polar ones, and we'll use a bulb to help us push the solvents through the column. The products have an orangish red color, so I'll represent them like this. And when we initially add them to the column, they'll all be mixed together. So we'll have the mono product, the di product, and possibly some unreacted ferrocene left over. We want to start eluting the column using a very non-polar solvent. So we'll start by using hexanes, which will dissolve everything, but start moving the ferrocene and separating it from the two products. Since ferrocene is very nonpolar, it's not going to interact with the alumina in the column very much at all, and will be moving the quickest out of the three compounds. And we'll keep adding that solvent until there's a clear separation between ferrocene and the two products, where we can move on to the second solvent, which is a 1-to-1 ratio between methylene chloride and hexane, which is slightly more polar than just hexane. Here we're going to see a couple things happen. We're going to see ferrocene start moving through the column a lot quicker, and it'll start coming out of the column, which we will gather in test tubes. And then we're going to start seeing a separation between the mono and di products as well. And we'll keep adding the solvent until there's a clear separation between the two, where we can move on to the third solvent, a 9-to-1 ratio between methylene chloride and hexane, which again is going to be slightly more polar. Eventually, the mono product will start to exit the column, and we want to keep eluting it until the mono product is nearly gone. At this point, we can add the last and most polar solvent, the 9-to-1 ratio between methylene chloride and methanol. And the reason why we wanted to wait until the mono product was nearly gone before adding this solvent is because it basically flushes anything out of the column. The di product will start to move nearly as fast as the solvent moves, and we wouldn't want it to catch up to the mono product and get contaminated all over again. But now we can just keep adding that solvent until the di product exits the column as well. Here's what the test tubes will look like once we're done eluting the column and gathered all the solvent. At first, we had some ferrocene come out. That's why there's a slight yellow color in those test tubes. Then a test tube with just solvent in between the ferrocene and the mono product. Then we had the mono product coming out, some solvent in between the two products, and finally, we had the diacetylferrocene coming out of the column. Now, we want to test the purity of each fraction, or each of the test tubes, to make sure that they all only contain one of the products. To do this, we'll be running a TLC for each fraction that contains product. We don't have to worry about the ones that only have solvent. So pure fractions on a TLC plate would look like this, where each spot only has one compound. If a TLC plate ended up looking like this, then we would have an issue with number 2. It would contain both the mono and the di product in it, and we wouldn't want to combine it with the other fractions that are pure. Fractions that are pure can be combined and the solvent evaporated, and then we can characterize the pure products by taking their melting points and running IR specs. I'll start by adding all of the reagents. So I'll weigh out 150 milligrams of aluminum chloride and add that to a 5 milliliter conical vial containing a large spin vane. Then I'll add 2 milliliters of methylene chloride that has been dried over sodium sulfate and left in the hood to make sure that there's no water contamination. And I'll set up the apparatus now so I can add the rest of the reagents with a needle and a syringe. I'll get 80 microliters of acetyl chloride and add that to the conical vial as well. And finally, I can add the ferrocene, so I'll weigh out 100 milligrams of that, and I'm going to be dissolving it in a milliliter and a half of methylene chloride, so I'll put it in a dram vial where I can later add the methylene chloride to dissolve it. Once the ferrocene is fully dissolved, I'll be adding it to the conical vial using a needle and syringe again, and this is where I'm expecting to see a purple color once it's added. So that looks great. This means that I don't have to start the reaction over, so that's nice. And now we can just let that react at room temperature for about 15 to 20 minutes. Once that time has passed, I'll remove the drying tube and the Claisen head adapter and start preparing the test tube with ice so that we can quench the reaction. I'll fill it about 2/3 the way up with ice and then begin transferring the solution over. Now I can get the sodium hydroxide to add to that solution and begin neutralizing the acids that were produced. And I'll want to stir that solution once adding the base to make sure that it reacts with all of the acid in there. After a little bit, I'll test the pH to see if it's been neutralized yet, which it doesn't look like it's quite there, so I'm going to go ahead and add some more base and keep stirring. I'll test the pH once again, and this time it looks like it's basic, which is okay because ketones are pretty stable in basic conditions, so we're good to move on now. I'll mix the phases together pretty well for a little bit, and then I'll start removing the methylene chloride layer and transferring it to a 25 milliliter Erlenmeyer flask. I'll get a separate test tube with some methylene chloride so I can begin the extractions, and I'll extract the solution 3 times just to make sure that I get as much product out of it as possible. And you can see as the extractions continue that the methylene chloride layer gets more and more dilute, meaning that there is less product to extract each time. Now I'll dry the extracts using sodium sulfate until it's free flowing, and it was hard to separate the organic layer from the aqueous one, so I'll probably have to add quite a bit. But once it's free flowing, I'll remove the methylene chloride solution, and since I had to add quite a bit of sodium sulfate, I'll rinse it a couple times with methylene chloride to reclaim any product that was left behind. To make sure that both products were actually produced, I'll spot a TLC plate, and then I'll use methylene chloride as a solvent to run it with 5 drops of methanol. And here you can already see that there are 2 compounds on each of the spots I made on the TLC plate, so that's a good sign that both products were formed and we can expect to have a separation during the column. Here's how the TLC plate turned out once it was finished. The lower dots would be for the dye product since it is more polar, and the top ones would be for the mono product. Now I'll just evaporate off the solvent until there's about 2 milliliters left at the bottom of the Erlenmeyer flask, and then I'll be adding 500 milligrams of the neutral alumina, which is the same stuff that we'll be adding to the column to separate the compounds. This helps make the evaporated products more as a sand-like solid, which is easier to handle and transfer, so it'll end up looking like this, and now it's ready to be transferred to the column. So I'll start setting that up. I'll start by adding the glass wool and getting it to the bottom of the column. And I'll start adding the rest of the components through a funnel, starting with the Ottawa sand, and I'll just need enough to cover the surface area of the column. From there, I'll be adding 8 to 10 inches of the alumina, and while I'm adding it, I'll just be tapping the side of the glass with some vacuum tubing to make sure that the alumina settles pretty well. This will just help with the separation of the 2 products. Once the alumina is all set in the column, I can move on to adding the product on top of it now. And finish by adding another layer of Ottawa sand. Here's a look at the 4 solvents that I'll be using throughout this process and that were discussed in the lecture portion. They are increasing in polarity from left to right, So I'll be starting with the least polar, being hexanes, and I'll go ahead and add that to the column now. You can see the product starting to dissolve here, and you can also see the solvent slowly moving through the column. I'm going to go ahead and speed up that process using a bulb. I'll create a seal as best as I can and start compressing to push the solvent through, making sure to break that seal before sucking air back into the bulb so as not to pull the solvents back up the column. It is really hard to see in this shot, but there's actually just a little bit of yellow color in the middle there, meaning that there's some ferrocene left over, and we can expect to see that coming out in the test tubes. But since there's a clear separation between the ferrocene and the products, I can go ahead and move on to the second solvent now. And we don't want the column to run dry, so I'll replenish the current solvent or add the next one before the current solvent reaches the sand above the product. Here I'm adding the second solvent, the 1:1 methylene chloride hexane solution, and now we're going to be able to see the monoproduct start to move through the column. At this point, solvent is starting to come out of the column, so I'll gather that in these test tubes. And keep pushing the solvent through until we see a clear separation between the two products. After a little bit, you can now see the yellowish ferrocene starting to come out of the column. And the two products are getting closer to being separated enough where we could move on to the third solvent. As the test tubes fill up, I'll just place a new one under the column so that we can keep going. And now it looks like there's clear alumina between the two products, so we are ready to move on to the third solvent, which is the 9:1 methylene chloride hexane solution. I'll keep pushing the solvent through until we can see some orange come out, and from there I'm just going to be eluting the column until basically all of the monoproduct is completely out. Now, I'll actually be separating the monoproduct into multiple aliquots or multiple test tubes with just a few milliliters each. And that's just in case there is contamination that comes out with the monoproduct. It's more likely to be only placed into one test tube with a small amount of product rather than contaminating the entire monoproduct that comes out. Now, in this lab, that's probably not super pertinent or necessary since the products are both colored and because there's a clear separation between the two products in the column, but this technique will be more useful in a future lab when it's more difficult to distinguish when there is a switch between one product to the next coming out of the column, and it will help us minimize contamination. So now I'll just basically be doing this until the solvent that is coming out of the column is basically just clear, like shown here. But now we are ready for the fourth and final solvent, which is the 9:1 methylene chloride methanol solution, which, as you can see, moves the dye product pretty quickly through the column and is why we wanted to have the monoproduct pretty much removed before adding it. Eventually it'll start coming out of the column, and we'll keep pushing the solvent through until what's coming out is no longer colored and just clear. Once the dye product is out, I'll dry the column by pushing all of the solvent out and can clean it by removing everything in there and placing it in the desiccant waste. I've gone ahead and numbered all of the fractions 1 through 13 and can start testing for purity by running TLC plates on the ones that have product in them. So for the monoproduct, that would be fractions 4 through 9, and for the dye product, that would be fraction 12. Here I have the TLC plates numbered and spotted, and I'll be running them using methylene chloride and 5 drops of methanol as the mobile phase again. And it looks like each of them is pure. I only see one compound for each of the spots, so I can go ahead and combine all of the fractions for the monoproduct and evaporate the solvent. And I'll add the dye product into a beaker as well for a quicker evaporation and start evaporating the solvent in both beakers using a stream of air and gentle warming. Here's what the separated products look like. The left beaker containing the monoacetylferrocene and the right beaker containing the diacetylferrocene. And now we're ready to characterize both of them. I'll first weigh out the two products so that we can calculate a percent yield. I'll start with the mono product and then I'll do the di product. But just remember when calculating your percent yield that is going to be a 1-to-1 ratio from the ferrocene to the monoacetylferrocene and a 1-to-1 ratio from the ferrocene to the diacetylferrocene as well. Here's the melting point range for the mono product. As always, I started at a few degrees lower just in case there was impurity, but it didn't start melting until around 81.1 degrees Celsius and didn't finish until about 82.0, so that's looking pretty spot on. Now I'll run an IR spec using the neutral mole technique since it's a solid product. And it looks pretty good. We see the obvious carbonyl peak that we should be looking out for, and then some sp2 hybridized carbon to hydrogen bonds there as well. Now the IR for the di product isn't going to be very different from this at all because it's going to have the same functional groups on the molecule, so the melting point is what's really going to help us distinguish the two. So let's go ahead and take that melting point, starting a few degrees lower as usual just in case. But this compound doesn't start melting until about 124.4 degrees Celsius and doesn't finish until 125.6. So a little bit lower than expected, but that's not too bad. And I'll run an IR for the di product as well, using the neutral mole technique again. And we're expecting to see the same peaks. And it looks like we do. We see the carbonyl peak, which we were expecting. So this turned out pretty well for the di product as well.